in this class, let us go further and peer into detail about the plot that we just saw in the previous view graphs. Okay. So, the etalon or the Fabry-Perot interferometer has this very important physical aspect called the free spectral range. So, the free spectral range is essentially the frequency or wavelength range between successive transmission maxima in the cavity. Okay. I am using the word cavity. So, cavity, resonator, Fabry-Perot interferometer, for us in this discussion these are identical. Okay. So, cavity, resonator or Fabry-Perot interferometer or FP etalon or just etalon, all these are the same. Maybe to cavity and resonator we can prefix the adjective optical, because we are talking about optical resonators entirely in this discussion. Okay. So, for the Fabry-Perot interferometer, the transmittance that we see over here, okay, essentially on the horizontal axis has a phase factor or a frequency factor. Remember, earlier we wrote this frequency factor as, we called this nu 0, we called this nu 1, nu 2, nu 3. This was nu, let us use the index q which we had in the earlier slides, recall, could take values 0, plus 1 or minus 1, plus 2 or minus 2, plus 3 or minus 3, and so on. So, we have nu or minus 1, nu or minus 2, nu minus 3 in its index, and so on and so forth, right. So, this was the transmittance of the cavity. Here we have chosen to make the plot of the transmittance look more like the real world transmittance which we showed, right, in the measurement that I had shown you earlier. So, it is of course modulated by the envelope which I requested you to give some thought about in this class. So, all the transmittances at each of these resonances, the maxima are not unity, they are some finite value, rather finite value distinct from unity. Okay. I am not even sort of putting a scale on the y axis. So, that is partly deliberate to emphasize the fact that these are more real world transmittances, they need not be unity. Okay. But then these green peaks correspond to resonant modes of the cavity, right. So, these are the modes of the cavity or the Fabry-Perot interferometer. Okay. Now, the frequency separation between any two successive cavity modes is called the free spectral range. Free spectral range is abbreviated as FSR. So, as a matter of my habit, I will start calling this FSR. Okay. Let us also get used to abbreviations which make us sound a lot more professional maybe. So, the free spectral range is essentially the spacing between two maxima or either in terms of frequency or wavelength. In terms of frequency, this is easy to read off. I have written these frequencies now in units of the cavity round trip time t. So, t is cavity round trip time. Okay. So, how do we get the cavity round trip time? We had L, which was the cavity round trip path length. So, take L. So, T is essentially the cavity round trip path divided by V, the velocity of light in this particular cavity. Okay. Is that good? Okay, fine. So, now the scale that was calibrated in terms of nu is written in terms of t, it is also now written in terms of the angular frequency omega by multiplying multiplying each nu by 2 pi. Okay. So, nu is equal to 2 pi, sorry, omega is equal to 2 pi multiplying nu, but nu is nu sub q. So, we have 2 pi multiplying q multiplying 1 over t. So, that gives us nu q's. We should possibly use the subscript for omegas and nu's identically. If I do this just from visual representation over here, it is clear that the free spectral range, which we call delta FSR, here delta FSR is simply 2 pi over t. Identically across, you take any pair of these peaks and the spacing between them is 2 pi over t. Okay. But what is t? I have used the symbol v for velocity here, but if it is in vacuum, we typically use c for the speed of light, which is what is used throughout. So, let us write down t as t is equal to L by c, and if we do that, then t being L by c, delta nu FSR is simply 2 pi c by L. Okay. Now, our job is simply to express this in terms of lambda, the wavelength. Okay. Why so? Because first of all, wavelength and frequency are sort of equal descriptions of an electromagnetic wave, they are related through the velocity, right. But then there could be scenarios, especially in a laboratory, where you predominantly have an instrument that can measure wavelengths. A spectrometer, a conventional spectrometer actually is ready to measure wavelengths rather than record frequencies. Just a second. These two are not the same, although mathematically it seems c is equal to nu lambda and spatial and temporal periodicities are interrelated to each other. When it comes to practically making a measurement, it is not quite the same. Okay. So, for those of you who have some background in optics, you can separate wavelengths by dispersing light somehow and ensuring that a beam that has multiple wavelengths propagating into it, and now sketching something at the bottom right of my screen. So, you take a device, whatever it might be, if your input beam had wavelengths all the way from lambda 1 to say lambda n co-propagating coherently in the form of one beam, you could have a device that can send each of these different wavelengths say all the way to lambda n into different directions in space. So, you converted the wavelength information into spatial information, and you could then have a detector with n pixels which records this, all right, and this entire setup would be a spectrometer. We convert wavelength information into spatial information and do the entire thing in spatial domain. Okay. So, therefore, this is a spectrometer. Frequency measurement is altogether a different concept and business in itself. It is another matter that we can convert from frequency to wavelength, provided we know these properties of the light beam as well as the material medium through which it is propagating. We know the medium and other things that the wavelength separation device, which I have sketched here, this mystery device is made of, but it is not really a mystery, because almost any student of physics or engineering understands that this device could even be a prism for a simple implementation, simple and very effective implementation at that. But for if you demand more from your spectrometer, the spectrometer may have to be involve, instead of a prism, it could involve one or more gratings, which are devices with periodic rulings on them and so on, right. So, let that be what it is, but our idea here is to simply convert the FSR, the frequency free spectral range, from the frequency domain, that is domain of nu and omega, into the domain of lambda, the wavelength. Okay. But we of course know that C is nu lambda, right. So, since C is nu lambda, lambda is C by nu, or nu is C by lambda, we can essentially write down delta lambda, the total derivative of lambda, in terms of the total derivative of omega or nu, as the case may be over here. So, with a little bit of elementary calculus, we can figure the following out, that is delta lambda and delta omega are related through this term lambda square by 2 pi c, which is the Jacobian of the transformation from omega to nu. So, if there are any questions about this is something we can explicitly discuss in a tutorial. So, I would request the TA to make note of maybe a discussion on the Jacobian of going from nu to lambda or omega to lambda, which could possibly be quite straightforward for many of you guys in the audience too. Okay. So, the point here is that I can write down the FSR in terms of omega, I can write in terms of lambda, and spectroscopists also like to use this quantity 1 over lambda, right, as another thing, as if we are short of terminology in life, right. But this 1 over lambda quantity is called the wave number, which I have also been referring to for k. K is actually 2 pi times 1 over lambda. 1 over lambda is technically the wave number. So, wave number is a favorite of spectroscopists, a very popular unit of describing frequency in spectroscopy, particularly in units of, often in infrared spectroscopy, centimeter inverse. The reason for this being, if I wanted to write things down on a frequency scale, and I really started to write this down in terms of absolute or other frequencies, which are absolute in any case, but in terms of numbers of frequency in terms of hertz or per second, these would involve very large numbers like 10 to the 13, 10 to the 14 and so on, which is quite painful and cumbersome, apart from the fact, more importantly, that it does not help us to get an intuitive feel for things, right. If I were to ask you to express all energies in joules, not many quantities would essentially come out with a reasonable number of joules of energy, right. So, indeed then it would be 10 to the minus something times 10 to the minus 19 joules, which is now starting to look like the charge of the electron. So, electron volts becomes a very popular unit in certain domains, like a visible photon has an energy which is few electron volts. Now, it is better to think about it that way, maybe psychologically, at least for us, than think about it in terms of something 10 to the minus 19 joules or whatever. So, electron volts is very popular. Likewise, the wave number again in spectroscopy identically again plays the same role. In fact, in spectroscopy using electron volts is also very popular for the frequency scale, because h nu turns out to be an energy which you may relate to. But treat that as a little digression, all in some sense targeted towards explaining as to why we should express this important quantity, the free spectral range or FSR, in terms of three apparently different quantities, which are the wavelength, the frequency and the wave number. All that you need to, and it pays to remember this, that wave number and frequency are linearly related as they are to the round trip phase in itself, and that wavelength that we often find most convenient to measure is slightly the odd person out, in that wavelength is inversely related to this phase, and hence this scale plotted in terms of wavelength could in fact look a little different. So, delta nu or delta omega FSR is 2 pi times c by L, but delta nu FSR is just c by L, the velocity of light divided by the round trip optical path length is the free spectral range, whereas delta lambda is lambda square multiplying 1 over L. Okay. A little tip, a trick for your tests and whatever, match the dimensions on either side. Delta lambda has units of length, therefore, the quantity on the right, which anyway should contain a 1 over L, gets multiplied by lambda square. So, there is some method to that, and likewise FSR expressed in terms of wave numbers is simply 1 over L. Okay. The C is not quite there, because that is knocked out in the math. Okay. So, this is something which I indeed had a little, let me just take this off. Indeed, the way to doing the Jacobian here is also on my view graph. So, d lambda by d omega, do the derivative, it is minus 2 pi c divided by omega square, this is equal to minus 2 pi c. Now, express omega square in terms of lambda, this is c by lambda multiplying 2 pi, that is 2 pi times nu, square that, and you get lambda square divided by 2 pi c to be the Jacobian of this transformation. All right.